first, I'd like to acknowledge the support from the ETD. And this was a project for a year, starting from ground zero. And this is kind of the 1 year, at the end of 1 year, that kind of progress report. My co-PI is Professor Lieven Vandenberg. He's an expert in optimization in electrical engineering at UCLA, and I'm at mechanical and aerospace engineering at UCLA. And two graduate students were on this project, and obviously, you know, student prepare these slides, otherwise I'll put their names on. Okay, so this project is about the control at the power control layer of the microgrid. And the objective, and the grid has 3 modes of operations: grid tied, off grid, and during the transitions. Our objective is to have superior power qualities in all modes of operations, and also provide seamless transition during the grid tied and off grid transition. And so a typical microgrid could be like this. It has a number of distributed energy source, and then there's a converter, power converter controls, DC to DC, DC to AC, all kinds of combination you can have. And then there will be a switch to connect this bus either to grid or disconnected. And so when it's disconnected, it's isolated mode, and then there will be load here. And so the project we do is we actually, this is the kind of architecture we build. We build the models, and this is all simulation work, no hardware. And when it comes to hardware, I'll mention that. So we build model for microturbine, wind turbine, and PV and battery. And then we also have the model for the converter, power converter, and those converters are at 100 kilohertz switch and frequencies. And so the control is really the pulse width modulation of those switches. And then there are loads, and right now in this work, all the loads were resistive loads, and it's interesting that it was mentioned in the previous talk about reactive load, and certainly that would have certain aspect impact on the control design here. And of course, the grid, this could be connected or not connected to the grid. And so each DER has some local control here, and the local control must be able to track sinusoids, that 60 hertz sinusoid, without significant error. Okay. And so we work on a particular control algorithm and compare with other popular control algorithm to see what's the effect of this control algorithm. And in a sense, that control algorithm is able to do what the previous speaker talked about, like harmonic tracking and like rejection of unwanted harmonics. Okay, so in a more control block diagram flavor, this is the kind of the architecture we have. We have local DERs. Each has some local power converter control, like this. And then there will be a kind of a upper layer control that control how much power each unit should generate or take. And so that's the kind of 2-layer control structures. We work on both, but today I want to talk mainly about this control on this layer to generate a pure sinusoidal wave at the right phase. And so the first task was to build the model for all those 4 DERs. And this is just a picture of one of it. And the way we do it is we look at the literature and build what we call average model, because this is a high frequency switching. And the average model is taking the average over the switching frequency. And so this is a very standard so-called state space representation of this windmill, and also windmill and PV are actually very similar. The control variable is actually this D1 and D2, those duty cycles. So you can see this, although it looks like a linear equation, it's actually nonlinear systems because the control enter this matrix here. It's not on the right-hand side as typical for linear systems. The other thing is that there's always these LCL filters and that people use to try to buffer the DR with the power electronic circuit. And this is another model for microturbine, and this is just the way the form look like. Okay. And battery, this battery model, what we care more about is the power converter part, and the battery part is the simplest you can do. It's just a source with the internal resistors, but it captured the main part of converting, including this switching device, switchers, and the LCL circuits. And this is also the equations. Again, the control variables is nonlinear, coupled to the state variables of the systems. And of course, because of these LCL filters, it generates a resonance. And this resonance, from control point of view, is kind of hard to deal with. And so, so the way we I'll show you how we deal with that. Okay, but the other thing is to construct this microgrid dynamic model by combining all these components, each DER's model together, and be able to switch between the off-grid and grid-tied grid modes. This is the structure we came up with. You have these 4 models here, and depending on whether it's, let's say it's island mode or grid mode, you just need to make a switch here. And so this is just current summation for the bus. And when it's in grid mode, because grid mode has a voltage reference, and so we don't have a feedback of this voltage. It's just directly take the grid mode voltage. But if it's in iron mode, we switch to that. Then depending on the load, right now it's just a resistive load. Of course, it could be a reactive load. Then this load is going to determine the voltage that fit into the grid, each DR in the grid. And so from the system model point of view, is like it looks like this, that X are the big states, or the aggregation of the state on each things. And so you can see that we have 4 DRs and in the diagonal terms, and also the input side. So there's a battery, PV, wind, and microturbine. The interesting thing here is that if we are in the grid-tied mode, then all this E is actually zero matrices, which means that these four DRs are decoupled, right? But in the island mode, because of this feedback, each of these E is actually this term, which is mostly 0, but there's this coupling term of this guy is related to a resistor and the inductor in this in the filter the ILR filter, right? So, but the good thing is that the structure is very clear in both the equation, how it shows the coupling, and so island mode in the control, the power converter control of island mode, will be more challenging than the grid connected mode. This shows the typical way people would do the power electronic control. There's for PV and windmill and for microturbine. For PV and windmill, typically we have this MPPT, the maximum power point tracking, to just get maximum power out of this power source. This is not our focus here. Our focus is really the inverter control. So we are concerned with this current mode control here to control the duty cycle of the inverter. And same thing for microturbine control. There's a speed control for the mechanical device to generate the voltage reference. But our focus is really in this inner loop here, this inverter control here. All right. And of course, so those 3 GR, and then we also have the battery, the current loop for energy source. Energy source here is battery. And so this diagram shows actually there are 2 loops. One is a very fast a PI loop here, that generate the sine wave reference, and the other is our control to track that current sine wave. And so again, our focus is here, assuming this would generate the demand. Okay. So the overall grid control is the diagram that shows the bus, and then it has this the inverter control on each loop, in addition to other control that generate the maximum powers. Okay, and so this again shows the equations that shows the decoupling and couple effect in the two different modes. So in the grid connected mode, this is the equation, and this is actually a linearized equation now of the nonlinear system I show. Now the control is the duty cycle here. So you can see this is actually a linear system for each DR, and then you aggregate these 4 DR, they won't have coupling. But if you have the islanded mode, then you have this coupling here that this is each DR, but it has coupling from other sources also. And so the question is, how strong is this coupling? Because when we design the controller, inverter control for each DR, hopefully we want to do decentralized control. We don't want to have communications between each DR. The lesson we learned is that if we just, because our students are like expert in tuning PID control, right? So when they try to tune the PID control for each DR under this setup for the islanded mode, they were not successful, mainly because of that peak resonance. They couldn't do it. So we have to do something more model-based, right? It's not tuned. And so the way we did it was we did this linear quadratic optimal control design, and LQ or LQI. I just means that we also add the integral mode in it. And if you know that this linear optimal control is a form of robust control. So this linear optimal control was designed as if, for the islanded mode, as if each DR were decoupled. We didn't include that the coupling from the load. And by doing this, we were successful in stabilizing the system, and I'll show you the performance. And so the good news is that we could still do decentralized control for this islanded mode, even though islanded mode is the HDR, the whole system is coupled. But the other message is that you cannot just try to tune it and hope it will work. It's hard, okay? Okay, so this shows that applying the decentralized linear quadratic controls, the green line is the open loop, so it shows this big resonance. And after we close the loop for each DR, that's the blue line. So there are four DRs, right? So it's a kind of a 4x4, and you also show the coupling. So the main diagonals are the each itself, and then the coupling effect can be shown by off-diagonal terms. And this is Bode plot. This is frequency response, the magnitude part. Okay, so in terms of quality, this is what we like to do is because the harmonic, AC harmonics is mainly the 60 hertz we want to track, and because the system is nonlinear, so it could generate higher harmonics, and so we want to make sure the signal is as clean as possible, the power is as clean as possible. And so the approach we do is the so-called repetitive controls. So repetitive control, the control is actually very simple form. It's kind of delay feedback, okay? And so in terms of computation, it doesn't really complicate the system. It just needs a little bit more memory for the delay buffers. But the effect is that it's able to track all the Fourier harmonics, in principle, all the Fourier harmonics of the basic frequency, say 60 hertz, okay? In practice, it can do maybe 10 to 20 harmonics instead of all the Fourier harmonics. Okay, and I won't get into how the control is designed, but I would like to show you the results. Before I show you the results, the way we do simulation is we set up a hardware-in-the-loop simulation where all the controller, like repetitive control, LQ controllers, was in one real-time controller, And then the DR simulation is in another computer. And so the communication between the controller and communication is through a real hardware wires. All right, through PWM and A to D, D to A things, okay? So just one slide to show how the hardware in the loop simulation is close to offline simulation. The difference is hardware in the loop simulation was average model. It's not doing this 100 kilohertz cycles. Offline simulation was doing this real 100 hertz switching. But you can see that they are actually very close with each other. And that kind of justify our hardware in the loop simulations. So this slide shows really the transition from grid-tied mode to island mode when we try to track a sine wave, what the error looks like. So at 2-second mark, the grid-tied was switched to islanding mode. And so with linear quadratic control, it generates spikes and then create a sustained errors, 60 hertz errors. Of course, we assume that before that there was no errors, okay? But with this repetitive control that was able to track these Fourier harmonics, the transition is fairly smooth. It doesn't generate, this is the error part. This is not the whole waveform. So it only generates a little bit blip. And it usually, it takes about 1 or 2 cycles to learn. 1 or 2 cycles of 60 hertz waveform to learn the profile. And so this shows this, what we call seamless transition when we switch from one mode to the other mode. Okay. And this is in the island mode voltage tracking that the repetitive control is able to track the phase very precisely. So you can see that this is easier to see the error. So the blue one is the linear quadratic is not able to track precisely. Mainly the error is the phase error, but the repetitive control is able to track the error, the phase very precisely, and error goes to 0. And not only is able to make the phase track precisely, but because this whole thing is nonlinear system, you have high harmonics, and repetitive control is also able to eliminate those high harmonics. So for example, in this simulation, it shows that the third harmonics component is prominent, and so the repetitive control does not have that part, the red one. This is in the frequency domain, and this is the 4DR. Another interesting thing is that in some cases here, the repetitive control was not able to kill that third harmonics, and this is because if you remember, we had that outer loop voltage generator, and that outer loop was PI control. It was not clean, and that outer loop did not generate pure sine wave. It has this third harmonic that it asks repetitive control to track, and that's why. So a solution of this would be also doing repetitive control on that outer loop. We didn't do that part. Okay, how does this repetitive control that can do precise tracking or waveform impact powers? So this is a simulation shows that the power demand, this is actually power, not voltage. Power demand switch from 0 to 3000 as a reference. And so if we do the regular LQR, because of the error, it couldn't generate the precise power. But if we do the repetitive, it generates the precise power. It follows the power command precisely. And of course, if we start to talk about higher and higher level power management and power distributions, being able to distribute and precise power would be important capability at the lower level, right? Lastly, we did some simulations to show what's the effect. So what I showed was like power grid transition, and in island mode or connected mode, how the response look like. This is a kind of case simulation to show when within, this is a grid connected mode simulation, when we have change of power distribution in the 4 different DRs, what is the transient look like? And so for example, in this case, the battery was switched from 1500 to minus was 1500, right? And then like at 4 seconds, PV generation was switched because of the irradiance. And so we do this kind of scenario simulation to see how the transient looks like. And of course, this transient is important to us. And these are all by feedback control. It does not have any predictive capability. It's all feedback control. So you can see that this is probably not very acceptable when we do the kind of very dramatic, drastic switch, a step type of switch. This suggests that the control need to have some kind of predictive capability. So for example, maybe PV power grid need to know in the next 5 seconds it will switch, and you will prepare for that. And that's a predictive effect. This shows another simulation for islanding mode. And again, but the interesting thing is when the battery, when the PV power reduced, battery power would make up for that, right? And of course, this is by the higher level power management that give the reference power to each DER. But the interesting thing is we found that the transient is still important, and just by feedback control, it won't be sufficient. It has to have, kind of forecasting, or when there's a kind of switch, the management would tell the DR, I'm going to switch in the next 10 seconds, exactly when, and then this kind of thing would be able to reduce its spikes. Okay, so just in conclusion, I show that from the modeling and looking at the models, we can conclude that in grid connected mode, the DERs are decoupled, so it's easy to design the controller. But but there's a coupling effect in the islanding mode, and they cannot be, you cannot do decentralized control by hand tuning, or it's very hard. And so, but fortunately, by doing model-based linear quadratic control, also based on decentralized control, this decoupled closed-loop system is stable, and it enables us to design a kind of a plug-in, add-on Rapadic control for the performance. And so the Rapadic control is able to generate zero tracking error. It eliminates higher harmonics. So in the simulation, we show it has a third harmonics. We also set up in our lab now the hardware converters. And in our test, we're seeing like harmonics of 3, 5, 7, 9, up to 9. So it has three or four more harmonics, and that Rapadic control can really handle that. So it will also show you a simulation that seamless transition is guaranteed, as opposed to if you just do linear quadratic, it has this spike and then sustained errors. The power spectrum from hardware in the loop simulation also show that, I already tell you that it's able to eliminate higher harmonics to guarantee power qualities. And of course, all this simulation was assuming resistive load. It will be interesting to know, to kind of investigate what is the effect if it was reactive load. Would we still be able to do kind of a robust control for reactive load using the same approach for the linear quadratic robust control approach? And that's kind of a question that I don't know the answers. Thank you.
Thank you very much.